Hello everyone, we are solving question number 49 of GATE 2019 chemical engineering paper related to process control and instrumentation subject. And the question is, for the closed loop system shown in figure, the phase margin is dash. So for this given closed loop system, we have to find the phase margin. So let's take a look on the solution. So we define this phase margin, let's just call it as PM. So the phase margin is defined as 180 degree plus phi, where phi is the phase lag at gain crossover frequency, and we define this gain crossover frequency is that is the omega at which amplitude ratio is 1. So by using these correlations, we will be finding the phase margin of the given question. So let's just write the open loop transfer function of this given block diagram. So over here, the open loop transfer function will be GUL is equal to Kc into e raised to minus of 0.1 s upon 0.5 s plus 1. Now we can write the amplitude ratio of this transfer function, open loop transfer function, as amplitude ratio will be, so for Kc equal to 5, it will be 5. For this exponential or the dead term, e raised to minus 0.1 s, it will be simply 1. And now for this 1 upon 0.5 s plus 1, we can write it as 1 upon under root of omega square tau square plus 1, that is 0.5 omega whole square plus 1. Now we can simplify this as 5 upon under root of 0.25 omega square plus 1. Now for calculating this phase margin, we need to find the gain crossover gain. We need to find this phi at the gain crossover frequency, for which we need to find this omega. And for this gain crossover frequency, the amplitude ratio is 1. So we will be replacing the value of amplitude ratio as 1, finding the value of omega, and then calculating the phase lag to find the phase margin. So let's just put amplitude ratio as 1. So this will become 1 is equal to 5 upon under root of 0.25 omega square plus 1. So this will become 0.25 omega square plus 1 is equal to 25. That is omega square. We can write it as 24 into 4 is equal to 96. That is, we find this gain crossover frequency as under root of 96, that is 9.798. Now we can find the phase lag, that is phi. So it will be equal to, so it will be, so for this it will be simply 0, and for other two terms, that is for e raised to minus of 0.1 s, it will be 10 in it will be simply omega tau, and we need to convert it into degree. So this will be minus of 0.1 omega into 180 upon pi, and for 1 upon 0.5 s plus 1, it will be 10 inverse minus of omega tau. So that is, we can write it as 10 inverse minus of tau is 0.5 omega. So from here we can find this phase lag as, let's just replace the value, 0.1 into 9.798 into 180 upon pi plus tan inverse 0.5 into 9.798. So this will be equal to minus of 56.13. And this tan inverse minus of this entire term will be equal to minus of 78.46. With the phase lag, we will be finding it as minus of 134.60. Now phase margin, we can simply add 180 to it. That is 180 minus of 134.60. So we will be getting the phase margin as 45.40 degrees. So for the given system, we can write the phase margin in degrees as 45 degree, 45.4 degree.